In the previous lecture, we discussed about the Wilkinson power divider, and we saw that how the drawback of a 3-port network which is matched and reciprocal but has to be lossy, that loss is sort of exploited or utilized in a rather different way, in which we essentially make the isolation between the two arms of the divider or combiner perfect. That is, there is no transmission between ports 2 and 3. We saw that S23 and S32 are essentially 0 in case of a Wilkinson. Now, having discussed thus far about power dividers, we saw that whether it's a lossy power divider or a lossless one, we took the very straightforward and standard case of an equal split power divider. The question which therefore one may ask is that, do power dividers always have to be equal split? That is, if you recall, if I have a power divider which is equal split in case of the Wilkinson also, it looks like this. This is port 1, this is port 2, this is port 3, and there's a resistor between these two ports. What we saw was that in case of the Wilkinson, the S21 and S31 were essentially equal to minus j by root 2. So that means if I now take the insertion loss from port 1 to port 2, that would be minus 20 log to the base 10 mod of S21. That would be roughly about 3 dB. Likewise, I can talk about S31 also, that insertion loss will correspond to 3 dB. What we are seeing essentially is that the transmission coefficient at either side is around 3 dB. Well, the loss is 3 dB, so the transmission coefficient is minus 3 dB. So as you know, minus 3 dB has a very special significance. That is, it is indicative of half the power. So if there is some power input at port 1, that is P, the power that is output at port 2 will be P by 2, and this is P by 2. Same at port 3. So this is called as an equal split Wilkinson power divider. So obviously there are applications where we do not need equal split. There are cases when we may need to send more power towards port 2, less power towards port 3, or more power towards port 3, less power towards port 2. These kind of applications are also there. So in that case, one thing that can be done is, if I, let us say, want to send more power to port 3, then in that case I can immediately say that in case of the equal power divider, the arm impedances were both Z1. So therefore let us call these impedances now as Z02 and Z03. Now in general we can say for unequal split that Z02 and Z03 need not be equal. So if I want to send more power to port 3 and less power to port 2, then I can immediately say that if more power has to go to port 3, then the characteristic impedance of this line must be lower. This is important. This is very, very important. Because lower the characteristic impedance, higher will be the current in the transmission line, and for the same voltage that would indicate more power. So, having said this, Wilkinson also proposed a way to which you could take his original equal split power divider and convert it into an unequal split power divider. So he said, let this port feed line be Z0 and each of these lines be Z02 and Z03. And let us say again you connect a resistor over here of value R. Now, if you define a ratio, let us say there is some power input over here, that is P1, and there is some power output at port 2, let's call it as P2. And at port 3, there is some power output, call it as P3. So, if we define that the ratio between the power at port 3 and the power at port 2 is equal to some k square. So, if you take the root of k square, you will get k, which will essentially be a voltage ratio. So, if you take the power ratio of P3 with respect to P2, you can define this as something like a k square. So then Wilkinson actually proved that using this k square term or this k term, you can actually derive the expressions for Z02 and Z03. In case of the equal split power divider, there was only one Z1 and that value was root 2 times Z0. This we had proved in the previous lectures. So therefore, what Wilkinson said was Z02 would be equal to this quantity. K times 1 plus k square, the whole root times Z0. And Z03 will be Z0 times 1 plus k square divided by k cube. You can immediately see that if k is more than 1 or if k square is more than 1, that means P3 is more than P2. You can immediately see that Z02 will be more than Z03 because this quantity will always be more than 1 and this quantity will be less than 1. So this further proves our intuition that for more power to reach port 3, the characteristic impedance of the line connecting ports 1 to port 3 and port 1 to port 2, they cannot be the same, and where power is going more, the characteristic impedance of that connecting line must be lower. So this proof is done by Wilkinson and is a little beyond the scope of the course. But there is one catch. There is one catch over here. The network would then become unmatched. That is the drawback of the unequal split Wilkinson power divider. So, in order for port 1 to be matched to Z0, it is necessary that the terminating impedance at port 2 is essentially Z0 times K. And the terminating impedance at port 3 is Z0 by K. This is a very important thing to remember. The terminating impedances at ports 2 and 3 are now no longer Z0. I leave it to you as an exercise to prove that only if the impedances at ports 2 and 3, the terminating impedances are these two quantities, port 1 will see a matched impedance of Z0. This you can prove quite easily. So unequal split power dividers are also called as tappers. Unequal split power dividers are also called as tappers. So now we had discussed another form of or another example of three-port networks which can be matched, which can be lossless, but they are not reciprocal. That is a circulator. We will discuss very briefly about circulators. We will not get into the depth of circulators too much. So a circulator is a three-port device or a circuit where the input at port 1 is transferred into the output at port 2. If there is any input at port 2, that goes as output to port 3. And if there is any input at port 3, the output goes to port 1. So what this means is the symbol of a circulator essentially looks like this. A circle with a curved arrow. This is port 1, this is port 2, and this is port 3. Just to repeat, any input at port 1 is transferred into port 2 as output. Nothing comes at port 3. Any input at port 2 is transferred to port 3. Nothing comes out at port 1. And any input at port 3 comes as output to port 1 and nothing comes to port 2. So therefore, circulators in the conventional sense were made out of ferrite devices. We will not discuss ferrite devices. They have magnetic properties. So in a sense, we will just talk about what the circulator is doing as a function and what its S parameters look like. So if you have something like a unity gain circulator, we can very easily write its transmission coefficients. S21 is 1, S32 is 1, and S13 is also 1. So therefore its S parameter would look something like this. So the question now is, from an application point of view, where would we use such a kind of device? Well, the answer is very simple. Circulators are used in transceivers. Circulators are used in transceivers. That is, modern day communication systems consist of both transmitters and receivers on a single piece of board or silicon. And what usually happens is that since the transmission and reception take place at frequencies which are close by or in the same band range, a single antenna is often used for both transmission and reception. So in that case, if you have an antenna and let us say you have an amplifier which has to pump the power into the antenna for transmission, this is the transmission amplifier. So therefore, if I connect a circulator over here, whatever is the input at port 1 will exactly go to port 2 to the antenna. But if there is some received signal at port 2, that would go to port 3. And what should we connect at port 3? We should connect the receiving amplifier. This is the transmitting amplifier and this is the receiving amplifier. So for transceiver circuits that consist of a single antenna for both transmission and reception, a circulator is quite a useful device. What you can see from here, this matrix, is that the diagonal elements are 0, which means it's a matched network. And you can also prove that this matrix is a unitary matrix. That is, it satisfies the unitary property and therefore it is lossless. Modern day, however, circulators are not like this. Modern day circulators usually do not use ferrites because those were essentially very narrowband devices. They were essentially narrowband devices, and what was seen was that why not go for active elements where we can introduce some gain also. So these essentially are passive circulators. So essentially people said, why not introduce a gain element? Some gain element alpha, let's say for example. So then in that case, the S matrix would become something like this. The gain in every path is alpha. And if alpha is not equal to 1, you can prove that this is no longer a unitary matrix. So the moment you have some gain element, you have a loss also somewhere. So therefore, this kind of circulator is not lossy also. And these 3-port networks like the Wilkinson power divider, they are narrowband. Why? Because they again have the dependency of lambda by 4 on the length of the connecting lines. Ferrite circulators are also extremely narrowband, and there is a lot of research that is going on these days to make circulators more broadband, and several strides also have been made in this area where people have actually used amplifiers to make circulators. With this backdrop and discussion and understanding of 3-port networks, where we essentially made use of a number of techniques to analyze them. In particular, to analyze the Wilkinson power divider, we saw that the analysis was initially very tricky because of that triangular shape formed due to 2 connecting transmission lines and 1 resistor. what was effectively happening was that we had to break the circuit into two parts, and that is what is called as the even and odd mode analysis. We had discussed the even and odd mode analysis briefly in the previous lecture. Let us take one more look at it from an electromagnetic angle. If we look at it from an electromagnetic angle, we said this also in the previous lecture, that if you consider that there are two current carrying conductors, if the current is of equal magnitude in both the conductors with same direction, then it is something like the even mode. If the current is same in magnitude as the first conductor but is opposite in the direction, then it is equivalent of the odd mode. Now, what we can say is, if we look at two conductors like this, if the current, let us say, is traveling this way towards us, so you use the right hand thumb rule, you can see that the magnetic field would essentially curl this way. Likewise for this conductor also. So what is happening in the middle is, when the field lines from the two conductors essentially interact with each other. So on the left hand side, the direction of the field is over here, and on the right hand side, the direction of the field is essentially opposite. So if the two currents are equal in magnitude, let us say I and I, the field would essentially cancel out. The field cancels out in the midpoint. So if the magnetic field is essentially 0 in the middle, it also indicates that virtually there is no current. Or rather, if the magnetic field cancels out over here, as per Maxwell's equations, if you recall, if the magnetic field is essentially becoming 0, there can be no electric field also. The electric field would become 0 because of Ampere's law, and because of that, what would essentially happen in this middle is that there would be an open circuit. So as if magnetic field is 0, the net current associated with that magnetic field would also be 0. So therefore there would be an open circuit. Whatever the electric field is, that's not our concern at the moment. What is important to note is that the current would essentially become 0, which indicates the middle is kind of like a virtual open circuit. And that is the basis of the even mode. Whereas in the odd mode, if we again have these two conductors, so if let us say the current direction over here is I, and here it is the other way, going away from us. So here again the direction would be this way, but here the direction would now be this way. So in the middle, if I have the field lines from either side, for the left conductor the field direction would be this way, and on the right hand side the field direction would be like this. So therefore fields would now add up because they are in the same direction. That means there is a current maximum. There is a current maximum over here. Whereas, if there are two opposing currents which are perfectly out of phase, so let us say the phase of this current in terms of time is I of t, and this is some t minus, let's say 180 degrees, or I should say omega t. So if the two waves are perfectly out of phase, in the middle of the two conductors, the electric field would essentially become zero. So therefore that is like a virtual short circuit. Here the electric field will not be zero, or rather it need not be zero. So this is what the odd mode is, and this is something that we already know. What is important to note from here is that here something interesting is happening. Here the fields are essentially, the magnetic fields are essentially adding up. The magnetic field essentially is adding up. Now, using this concept, let us change the scenario slightly. Let us change the scenario slightly. Let us say I have two conductors which are placed side by side. And let us say in one conductor we have some current, some time varying current I of t. So obviously there will also be a time varying magnetic field. And let us say, for example, in this second conductor, I am not putting any current whatsoever. So the question is, what will happen? The question therefore is what will happen. If there is current in the first conductor and the second conductor has no current, and the second conductor is placed in close proximity to the first conductor, what will essentially happen is that this time varying magnetic field, which is around this time varying current element, will start interacting with this conductor also. And we know that whenever there is some time varying current across the dimensions of a conductor, some kind of a EMF is generated. That is Faraday's law, or one of the Maxwell's equations. So interestingly, what is happening is that we have revisited a phenomena which we were aware of since our high school days. That is the phenomena of electromagnetism or electromagnetic induction. Because of the current in this conductor, there is another current which is generated over here. And essentially this phenomena, you will see that there is some other current, let's call it as, if this is I1, then this will be I2 of t. This is the induced current. This is the induced current as a result of the field, the magnetic field around the first conductor interacting with the second conductor. Effectively, what we are noticing is because of this I1, there is an I2 which is induced, which otherwise was not there in this conductor. This I2 is not externally supplied. This I2 is induced in this conductor, because solely due to the current in the first conductor, there is no source that is used to drive the second conductor. While this is called electromagnetic induction, there is one more term for it, and this is called as RF coupling. Now, what this means is, RF coupling is very similar to electromagnetic induction, which means that if you have a conductor that is carrying some time varying current, then another time varying current can be induced in a conductor which is placed close to that first conductor. So, what this gives us is something very interesting. How is I2 related to I1? How is I2 related to I1? Definitely, I2 is proportional to I1 in magnitude. Obviously, the direction of I2 will be opposite because of the Lenz's law, which says that the direction of the induced current must always be opposing to the cause that is producing it. But all said and done, more the value of I1, more will be the value of I2, because more I1 means stronger will be the magnetic field. So the EMF or the induced current that will be in the second conductor will definitely be more. Now, where would we use this? Suppose I have an amplifier that is carrying an RF signal to an antenna. Suppose this antenna is connected to the amplifier, but we want to be sure as an engineer that indeed the amplifier is giving the proper output. So over here, let us define certain power quantities. Let us define power in dBm. This M stands for milli. So power in dBm is nothing but 10 log to the base 10 of the absolute power normalized to 1 milliwatts. Therefore, this dBm stands for dB milliwatts. So if the power is 1 milliwatt, if the absolute power is 1 milliwatt in dBm, it will be 0. So suppose there is a source which I have connected over here, and that is giving a power of about 0 dBm. Let us say the gain of this amplifier is 20 dB. Then the output power is expected to be 20 dBm. This is what we expect. So if the antenna is matched to the amplifier, we expect that the antenna should get that 20 dBm power in full. But if we have connected the amplifier to the antenna, we are not sure if the amplifier is indeed working and it is giving that 20 dBm output. How can we check it? Can we simply measure the voltage over here? Not really. Because as you know, at RF frequencies, any multimeter or any instrument that you connect over here would also act like a transmission line. And therefore, if I connect a probe over here, at this point, the antenna conductor and the probe conductor would start behaving like a power divider. And therefore, you will not be able to get an exact estimate of what the power is. Rather than physically connecting any instrument probe, what if I bring another conductor which is close physically to this line? So therefore, what I mean is this. So this line is carrying some wave and there is another conductor over here. If I do this, I am not disturbing this main line in any way, but rather what I am doing is I am inducing some current or some wave with whose magnitude is proportional to the wave in the first conductor. So this is called as coupling. Now what I can do, I can simply connect my instrument over here and measure the magnitude of the wave that is here. And if I know how closely these are spaced, by reading the magnitude of the wave in the second conductor, I can estimate how much is the magnitude of the wave in the first conductor. And thereby I can say that, okay, using this relationship, I can be satisfied whether the magnitude of the wave in the first conductor is as per our desired requirement or not. So therefore, coupling is a very widely used technique to probe the condition of a main transmission line without physically touching it and thereby causing some loading. Now let us look at this pair of conductors from a closer angle. Let us say I have a microstrip line. We know what is microstrip. The bottom conductor is ground. There is one conductor over here and another conductor over here which look like this, and these two run parallel to each other. These two are essentially running parallel to each other. So, can I treat each of these as a transmission line? Definitely I can treat it as a transmission line. So let us say we have this microstrip pair, two identical lines. We have two identical lines which are close to each other, but it is like saying there are two transmission lines which are actually close to each other. Now let us first consider the case when the two of them are carrying equal current in the same direction. So what we saw was, if there are two equal currents in these two conductors, in the middle somewhere there will be a virtual open, because this is the even mode. So along the midpoint somewhere there will be an open circuit, a virtual open circuit. So it's like saying, if there is an open circuit, it is almost like that these two lines are independent of each other. These two lines are independent of each other and therefore can be analyzed separately. So if I want to ask now, what is the characteristic impedance of each conductor? So what I can say, I can actually take a small section of this conductor, let's call it as some delta x, and if I now magnify this, I will see that essentially an inductor is running and in parallel there will be a capacitor. If you assume that this line is lossless, then this inductor will be L delta x and this capacitor will be C delta x. So therefore, the characteristic impedance of each line in the even mode, I can define it as something called as Z0E, and as per transmission line theory, we know that it is under root of L by C. L by C. So therefore, this quantity is called as the even mode characteristic impedance. Now let us look at something that is a little bit more difficult, and that is the odd mode. Same scenario, except what? Except that the currents are now in opposite directions. So the current over here is in this direction and the current here is in the opposite direction. Same magnitude but opposite direction or phase. So in the middle, as we know, there would exist a virtual short circuit because this is the odd mode. Now we can no longer say that these two are independent, because we saw that in the odd mode some interaction is actually happening between the two. Now how is that happening? We took the example of where there was this current in one conductor and there is no current in the other conductor. That is not the even mode, but there is certainly some component of the odd mode over there, and there the EMF is getting induced. So what is essentially happening is that due to this current, there is some electric field, let us say plus E over here, and due to the equal but opposing current, the electric field over here is minus E. Now when we have two electric fields, let us say I take a snapshot and freeze this in time, and at some point of time I am noticing that there is two conductors with equal and opposite electric fields, and there is no direct connection path between these two conductors. There is no direct connection path between these two conductors. So the question therefore is, how can we model the interaction between those two conductors in some kind of an electrical way? Well, I can say that some sort of capacitance is there between the two lines. Because as you know, capacitance exists when there are two conductors with opposing electric fields and no direct connection between the two. So there is some kind of capacitance which is formed in the odd mode between the two conductors, and therefore it is called as mutual capacitance. mutual capacitance. That is the capacitance between the two conductors. Just like the L and C, those were per unit length quantities in a transmission line. Even this mutual capacitance, let's call it a Cm, is a per unit length quantity. So now if I look at these two lines with a magnifying glass, what I will see first are the two conductors which are first independent. This is L delta x, this is L delta x, C delta x, and C delta x. Now, the mutual capacitance here will be what? It will be like this, Cm times delta x. Now, there is one more thing which we are forgetting. If there are two currents in magnitude and opposite in direction, somewhere in the middle there is a virtual short. So that means what I can do is I can represent this capacitance as a series connection of two capacitors. I can call this Cm as a series connection of two capacitors. Let's call it as 2Cm and 2Cm. And here I have connected a ground over here because in the midpoint we have a virtual short. The electric field essentially is becoming zero in the middle. So effectively what is happening? Now I can again treat each of these two conductors independently, because here also we have a ground, here also we have a ground, and here there is a ground. So each of these lines looks something like this. I have this C delta x, and in parallel I have this 2Cm delta x. So therefore the odd mode characteristic impedance is this, L by C plus 2Cm, because these two are now in parallel. So what we noticed? We have a Z0E and a Z0O. In case of closely spaced conductors, we can have two kinds of impedances. One is the even mode characteristic impedance, the other is the odd mode characteristic impedance. We remember that the even mode characteristic impedance is the same as that of an independent transmission line, that is under root of L by C. And this one, the odd mode characteristic impedance, is Z0O, which is L by the square root of L by C plus 2Cm. So here, since the denominator is more, I can say always that Z0O is always less than Z0E. Z0O is always less than Z0E. So, in today's lecture, we discussed about the unequal split Wilkinson power divider, and we started with the discussion on the basics of circulators and continued from there on into the basic electromagnetic phenomena behind what we call as coupling in RF structures. So whenever you have two conductors in close proximity, you will definitely have some amount of coupling. And we also related the coupling phenomena with our previously held knowledge of transmission lines that is the distributed per unit length quantities of a transmission line. We shall continue from this point onwards in the next lecture. Thank you.